Mr. Schultz here with you, and we're taking a look at 11.1.3 in CCA2. So let's take a look here. So in Chapter 9, we talked about randomly selecting some things and trying to avoid bias. We're going to kind of get into that with the situation about the latest phone, which is the Pi phone, which I think is amazingly awesome. The Pi phone, we're talking about what proportion of young people have the Pi phone. And we cannot possibly ask everybody in the United States who's between 12 and 20, but we can take a random sample of this population and calculate that we think that this proportion of them have that. So if a random sample of 1,000 members of our population, then 250 of them have the Pi phone, it still does not mean that exactly a quarter of them own the Pi phone. So this is kind of the idea that we're going to be talking about here is basically like, hey, and things we can't really measure like super perfectly, like a population of people that have a phone, or the population of an animal species, or something like that. We will do a sample, and then take that sample and take some and kind of use that to predict. But then we'll also kind of hedge our bets against that and say, okay, if I took 1,000 and 250 have that, I'm not going to say that every fourth person now in that group has that. I still have to kind of hedge that, and we're going to talk about that in this term here, margin of error, margin of error. So we'll talk about that, and basically what that is that you might read in the newspaper that percentage of teams with Pi phones is 23% with a margin of error of 3. What this means is that we can be reasonably certain that they're based on the sample, that somewhere between 20 and 26% of all teens own the Pi phone. And so what that was just taking that 3% and going off of that average there and saying that, hey, down to 20% and up to 26% and going from there. I probably shouldn't use the word average there. You read in the newspaper that the percentage of teens is this. It doesn't say if it's an average, but so that's kind of what we're going to be looking at today. Is basically taking a sample and then trying to figure out a margin of error so we can kind of do some predicting with it. So let's jump in. So this is a big thing, just to say that your teacher is going to hand you some candy, but guess what? I'm not going to, because I'm not that nice. And we're going to take samples of that, and everybody's going to get a bag, but I'm not actually going to do this. And then we'll take samples as to how many people get blue. But guess what? I couldn't find any data online about blue ones, so it's going to be how many yellow M&Ms are in the bag, which of course they call candy-coated chocolates and covered with C's, not M's, because they don't want to get sued for copyright. So let's jump into question number 27 here. So get a sample from your teacher and calculate the portion of yellow candies in your sample, and write your answer as a decimal. So I cooked this up into some spreadsheet funness here. So here's some spreadsheet. Here's all of our samples. So here's all your classmates. This classmate got a total of 18 M&Ms with 0 that were yellow. This one got 20 with 0 that were yellow, and so on and so forth. And way down here, this is going to be your sample because it's closest to my bottom. So 19 total M&Ms you got, with 7 of them being yellow. That decimal then I just rounded off is 0.37, or I shouldn't say rounded, I truncated it off there. So about 37% of your sample was yellow. So that is what happened to you in your data here. So write your answer as a decimal, 0.37. I should also say this. My answers are going to be different than the books because I'm using yellow, and there is a different rate between yellow and blue M&Ms. And so, yeah, you might see different answers here than what you probably will see different answers than what you see in the book. So just know that as you are watching this. So now it says use your calculator to make a histogram of all the proportions. The histogram is going to show the results of a sampling distribution. And so basically what that means is that we took samples. Everybody took samples of this, and they came up, and then we're going to put that all together into a graph, and we're going to call that good. So here's what we do to create that histogram. So when I'm making a histogram, I'm going to use Desmos. You can also do this in the TI. I just think that it's a little bit better in Desmos. So we're going to do Desmos. So I took all of those yellow numbers, and I just made them into this list. So, and I labeled my list L, just because sometimes you want to use your list for more than one thing. But so basically how you do that, you could label your list M, or maybe not, because it looks like it's mad at me. Let's call it L1 then, and we'd say, or let's see if it'll let me do this. M equals, and then you would just put that that bracket there, and you just start to put in all of your numbers. And notice here that it popped up, hey, this is a 2-element list. There are only 2 things there. So the cool thing about this is that if I put this list in here, and then I create this histogram, I forgot the T, histogram. Here we go. And then I can put that in and say, hey, I want list M to be in there. Now it made a new histogram, or I want list L to be in there, or I want some other list, and I can go and kind of change it out like quickly. So I have preloaded a ton of this stuff because you guys didn't need to see me type out a list of 25 numbers, but there's that. Here's something that I always dislike. It starts with the bin aligned being centered. So center on this line here is saying, hey, I've got 2 0 counts there. I always like them to be left. I just think it makes more sense to my head to say that, hey, this is 0, but that's a preference thing. You could absolutely do it like that, but I'll just tell you that you're wrong. Not actually, though. Okay, so I've got it left count here, and then there's some other buttons here that we'll mess with there. And then as far as bin width goes, that's just saying like just this is from 0 to 1, but not including 1. Here are all my 1s. Here are all my 2s, 3s. So I had 7 pieces. So 7 of the classmates had 3 yellow M&Ms in their package. Here was a year count of 7 yellow M&Ms, and you were one of 3 people that had that. So that's what the histogram is doing there. So pretty straightforward in Desmos. Just type in your list, and then just drop it in here. I didn't mention this. You could actually just type the list like right in here. Just be sure to use this this same type of bracket here, so that Desmos knows what you're trying to do with it, and so on and so forth. And then you can make your histogram like that too. Like I said, though, I tend to like to label it in a line and then put that line in here, because then if I need that list someplace else, I want to make a different type of thing, I want to make a box plot, something like that, I can just go, oh, here, I'm just going to go box plot, and I'm going to do a box plot based off of L. And now look at that. And I didn't have to retype anything or copy and paste. It is just faster. So that's that. There's our histogram. That was a long explanation for a pretty simple concept. But let's jump back to our work here and see what this looks like. So use your calculator to make a histogram of all those, and then go from there. Okay, we did that. We sketched it. What is the mean proportion for the whole class? This gives an estimate of the proportion of the yellow candies in the population. So something else that I didn't mention before I said this. So in our sample data here that I found in this spreadsheet, this is only 25 values, and yes, it's row 26 because my first row is my labels there. There are only 25 samples here. Normally, when you're doing a sampling distribution, you want to have at least 100 because you're just trying to get a high level so that you can be more accurate. The more samples you can get, the better accuracy you can have on your number. I only ran with 25 because that's the numbers that I found, and I didn't feel like making more up, and that's that. So jumping back here to this, what is the mean proportion for the whole class? Well, I think that you can figure that out. We just need to go and add up all of these totals, and then you need to divide, and then you need to add up all of the yellows, and you take the yellow divided by the total, and that'll give you your decimal. Good news in Excel, it's a formula. So I just did the sum here, and then I took the average of that. So there was an average of 18 M&Ms per package, and there's an average of just under 3 per package for that. So jumping back to our work here, we would say that our average here, the mean or the average of this would be about 2.96. We'll call it approximately 3 for that. So that gives the estimate of the proportion, of the proportion of yellow candies in the population. So we're thinking that on average, we are going to get about three yellow M&Ms in each little fun size package of M&Ms. Okay, so but going back to our original thing that we had at the front of this, where we said, hey, we wanted to know kind of what that the margin for error was, because not everything is going to hit at exactly 4. You know, clearly in our data, we had a lot of people that had more than 3. You know, we had all these people that had more than 3, and we had all these people that were less than 3. So like actually most of our data is not 3. So then we want to look at that. So it says we're interested in typical results, not the extreme ones. So we will call the middle 90% typical. Between what upper and lower bounds are the middle 90% of the yellow proportions. That is, 90% of the time we expect the population of yellow candies in the sample to be between this and this. So what this is saying is this, is that we want to try to cut off the extreme values because those can really have a pull on averages. So we want to take the center 90%. So if I've got 25 numbers and I need to find what the center 90 is, that means that I need 5% of the numbers below 2 to be gone, and I need 5% of the numbers above it to be gone. So I need the lowest 5%, and I need the highest 5%, and I need those two things to be gone. So in 25 numbers, that'd be about 2.5 of the numbers. So what that means to you is this, is that this is my low one, this is my low one, and then my average happens somewhere between here. So my lower bound is going to end up being 0.5%, or excuse me, 0.5 yellow. Whoops, that's not how you spell yellow. 0.5 yellow, because I'm dropping off these bottom two zeros here, and then 2.5 happens before I hit this 1, so I just take the average of those two numbers, which is 0.5. Then on the high end, well, I had 3 people that did 7, so this would be a low, or excuse me, this would be a high, this would be a high, and then my next one happens between these. So in this example, it doesn't really change a ton, because these 7s are going to stay the same. If I would have had a little bit more data, maybe I would have seen this drop down, and I might have dropped off this 7, but in this case, I didn't. So my upper bound is going to be at 7. So my lower bound was at 0.5, and my upper bound, whoops, I guess I should match that formatting, and my lower bound was at, or my lower bound is at 0.5, my upper bound is at 7. So that's basically what that question is asking for. Just basically take your 5% off of the bottom, 5% off, and take that top 5% off of the top, because we want to get rid of those extreme data points there if we can. Okay? So now here is that. So our numbers that we would fill in here is that we would expect the sample to be between 0.5 and 7. And that just is what it happens to be for our data. Again, we have a pretty small sample size with 25. You want to get 100, so our results are probably going to be a little bit more skewed than what you'd really want. So now here's our last step. Tell Abigail, who is our person who's pumped about the M&Ms, your prediction of the proportion of yellow candies given the margin of error. The margin of error is half the spread between the upper and lower bounds. Okay, so the spread between the upper and lower bounds would be 7 minus 0.5, so I get 6.5. So half of the spread would end up being, 3.25. So the margin of error is half of the spread between the upper and the lower bounds. And so here, so this is where you can tell that our data is not super great here, because we think it's going to be 3 plus or minus 3.25. So what that margin for error tells you is that you could either have anywhere from negative 0.25 of a yellow M&M up to 6.25 of a yellow M&M, which is kind of crazy and is why we use margin for error, because it can kind of tell you like, hey, do you have some data that's pretty wide ranging that you're not really sure about? Well, to say that you should get 3 M&Ms, just like we saw here, but then plus or minus 3 point, like your margin for error is bigger than the actual averages. So ideally, again, we would have done more numbers, but this kind of gets you that idea of saying, okay, I'm taking that spread and I'm dividing it by 2, and that is what's getting me my margin for error, and I take that with my average. So my average was this, plus or minus my margin for error tells me what our prediction is. We predict that you'll get somewhere between basically 0 and 6 yellow M&Ms in your package, which is a thing. All right, that's everything for this lesson. So review and preview, check that out. Let me know if you have any questions. Bye-bye.